Okay, so a couple of things that we're going to talk about with wave motion is that waves are energy. And of course the molecules move, but they don't move as the wave moves. And in fact, like water molecules will tend to go up and down or in circles in the ocean, whereas the waves are continuing from even maybe the middle of the ocean to a beach. It's the energy that's transferred, not the matter. And so we're really more interested in the energy generally when we do some calculations, and just realizing that the molecules of the matter, like the air molecules and the water molecules, or whatever the medium is that's transferring that energy, is interesting, but that's generally not what we're calculating. Okay, so when we calculate things, we are going to take wavelength times frequency, and that's going to equal the velocity of the wave. For electromagnetic radiation, all of light, from gamma all the way to radio waves, and visible in between there, microwaves, that kind of thing, ultraviolet, the waves are going to travel at the speed, the velocity of 3 times 10 to the 8th meters per second. Now there are two types of waves we're going to look at. Transverse, where the vibrations of the particles of the medium move perpendicular to the wave pattern, like water and strings. And we're going to look at a second type of waves, longitudinal waves, where the particles move parallel to the wave pattern, like sound waves. A couple of things too that we mentioned before. Waves can interfere. If their waves and troughs meet at the same point, then there's constructive interference, like resonance, and the wave becomes larger. If one wave's trough meets another one's crest, then there's destructive interference, and the amplitude is 0. They cancel each other out. And then of course there's in between there too, which we could talk about beats. I think we're going to skip a lot of this, but we'll hit on some important points here. We can set a wave up on a string, and we can set it up where the wave is sent down the string, reflects, comes back, and at some point the waves going and coming back constructively interfere and a standing wave is set up. And you have probably seen that if you play a stringed instrument at all, or have watched a video on that. Sound is longitudinal waves created by a vibrating object in a medium. So there has to be a medium of some sort, gas, liquid, solid. So when they say, in space no one can hear you scream, that is true because there's no medium for the waves to travel. Region of compressed medium is called condensation, and less compression or less pressure is rarefaction. We, again, probably are not going to spend a lot of time doing that, but that's just the back and forth, like an eardrum whose pressure differentials cause that eardrum to vibrate. Okay, so we're going to look at a couple of different things, string instruments, wind instruments, and how those standing waves are set up in those instruments. When we do stringed instruments, the pitch of a note is determined by the lowest resonant frequency, called the fundamental. And when we put a finger on the string to shorten the string, the pitch is higher since the wavelength of the fundamental is now shorter. The frequency will be higher. The strings are different masses, so velocities are different. And also do remember when we do the problems that velocity of waves on the string is not the velocity of sound in air. So just kind of keep that in mind. And then the heavier the string means more inertia, slower velocity, and lower pitch. And things like piano and harp have strings of different lengths, so you don't need to, like the violin or viola, have to put your finger exactly where a standing wave can be set up. I don't think we're going to spend a lot of time on speed of wave on a string. It's a fairly simple, straightforward formula, but I don't think I have any in the worksheet. And I think we're going to not do a lot of linear superposition yet either. Although those are interesting, if you watch the video, you can see how noise-canceling headphones work. So I think we're going to go ahead and skip through this. Standing waves. So let's go back to our standing waves. And I did not embed this YouTube video, so maybe just go to the YouTube video and watch it. yeah, I'll embed it for next time, but go ahead and just go to that link and watch the video. And you can see a standing wave being created there, and that's because the waves are constructively interfering. All right, so when we set that up on a string, what ends up happening is we're going to get our fundamental frequency, and our fundamental frequency is going to be half of a wavelength. And if you want to visualize that, maybe start with the second harmonic, because with the second harmonic, you have the length equal to the wavelength. So what we basically have here, let's look it up here. We have maybe the end where the string is fastened, and maybe your finger where you have it held down, or in a piano, it's what's happening. And you have the string going that way. Let me draw on this side. Okay, try to make that symmetrical and oval looking, and you have the idea. So if you are setting the second harmonic up, what is happening here is you have a length, the length of your string, or the length that you're making the string with your finger push there, is going to be one whole wavelength. So from A to equilibrium to negative A, back to equilibrium, back to positive A, or however you want to think that. So if you think of the first harmonic, the first standing wave, you're thinking about it like right there. So you place your finger right there, or the piano string is only this long, or whatnot, and you get the first standing wave. So as it's coming here, coming back, and as it does that, it completely 100% constructively interferes, and so you get a standing wave. And so our first type of standing wave is going to be 1/2 of that wavelength. The second is going to be equal to that wavelength, and then the third harmonic, and fourth, and so on. And we can draw pictures of all of that. We can then find the frequency by taking this value n as whatever harmonic we're looking at here, and the velocity of the wave on the string over 2L. So let's just take a look at an example here. Let's say that we have a wave traveling at 420 meters per second, and we have a string that's 0.6 meters long. So we would have length is equal to 1/2. Now the string is 0.6 meters long, and so our wavelength then has to be 1.2 meters, and then our frequency is going to be 420 meters per second divided by 2 times the length, 2L, and we're going to get 350 hertz. So our first harmonic is 350 hertz. Our second harmonic is going to come from that, and so we know that the length is 0.6, the wavelength is 0.6. Okay. The frequency is going to be 420 N over 2L, which is 0.6. Sorry, I should have put 0.6 in there. And you get 700 hertz. Okay, and our third harmonic. Okay, so if you, and you can go ahead and plug that in, if you play a stringed instrument and you ever take music theory, there's actually a lot of math there. Okay, so that's how we can set up what our frequencies are and how we know what our frequencies are for a stringed instrument. Wind instruments are going to set up a standing wave in a column of air within a tube. And if you've ever heard that vibrato in a human voice, a singing or a violin, of course that's strings, but you can set up vibrations of air within that column. And so we have some pictures, like I drew the picture before, so you could kind of see why this is the first harmonic. It's actually only 1/4 of that wavelength, and so our wavelengths will be 2 times the length. So there aren't tons of these anymore, but if you have a pipe organ in an old church, and I love going through old churches, they're so interesting to me, and seeing those old pipe organs, they just cost a fortune to upkeep, so they're going more and more out of fashion. If you ever have a chance to check those out, they're really, really cool. All right, so there is a difference if you have an open on both sides or a closed on one end. And so if we can do both of those, I'll do those pretty quickly. If we have an open versus if we have closed, okay, and we have a 26 centimeter pipe organ, it's 20 degrees Celsius, and sound will travel at 343 meters per second at 20 degrees Celsius. And so you always need to warm up an organ because otherwise it'll be off pitch. All right, so for an open, our fundamental is going to be 1/2 the wavelength. And so we could go 0.26 is the length. Okay, very similar to the other ones we did. And we're going to get a wavelength of 0.25 meters. What that means then, our frequency is going to be 343 meters per second, 0.52, we have 660 hertz. Okay. We can do our second harmonic. This is our first harmonic or our fundamental. Our second harmonic, or what's sometimes called the first overtone, is that. This is 0.26 meter. Our frequency would be 343 over 0.26, and we get a second overtone, or a second harmonic first overtone at 1,319 hertz. If it were closed, the length would equal, 1/4 wavelength, and then what we would say here is that our wavelength is 1.04 meters. Our frequency then would be 330 hertz if we took the 343 divided by the 1.04. We then go, that's actually our fundamental. We then actually go to our third harmonic, and you can kind of see from the pictures why that would be the third harmonic. The third harmonic is where the length is 3/4 of the wavelength, and so then our wavelength would be 0.35, and our frequency would be 990 hertz. Okay, I'm running out of room here, so for our fifth harmonic here, we'd end up with a wavelength of 0.208 and a frequency of 1,649 hertz. All right, so that's how you can figure out the fundamental and the first and second and third harmonics. All right, so we'll end there for this one, and we'll pick up with sound on the next one.